The artificial intelligent autonomous prototype demonstrates how it navigates by using the onboard global positioning satellite system, which includes the gyro and inertial measurement units, in order to provide navigation, direction, and vehicle inertial guidance with excellent accuracy. Quantum neuromorphic artificial intelligence platforms. The objective is to cover the following topic.
The cognitive, intuitive, artificial intelligence drone consists of a global positioning satellite system. This global positioning satellite system communicates with available satellite units in orbital space. As a result, the global positioning satellite system enables the artificial intelligence drone to provide mapping strategies and error correction and obstacle detection. The main objective is to present a sophisticated technology based on an autonomous artificial intelligence
Cognitive drone.
These are the remarkable, impressive capabilities of the artificial intelligence drone. For stabilization and orientation, it utilizes a 3x gyroscope and 3x accelerometer. For navigation, it has a magnetometer and a GPS antenna. The system also includes an onboard SD card for data logging. All of this is integrated in a small form factor. I also integrated a telemetry radio and airspeed sensor system. The telemetry radio connects the autopilot system to a laptop computer so you can monitor the drone. In an autonomous mode, the autopilot controls the servos. Inputs from the RC transmitter can outride the autopilot. Now let's talk about the software interface. There are several software models used to program and to monitor the flight. In this case, we use Mission Planner software. First, set the waypoints on the map. Waypoints include setting altitude, speed, and other actions. 2. Load the waypoints to your drone. And 3. Set the roll and pitch and yaw actions. 4. You can switch from manual to autonomous mode. In addition, telemetry logs are recorded and saved automatically on your laptop during each flight and after every flight. The airspeed sensor system allows for control of the drone based on airspeed instead of the ground speed, which comes from the GPS readings. The autopilot is connected between the RC receiver.
Autonomous robotics, motor methodology and applications. the rotor and stator magnetic field. The rotation is obtained based on the forces between two magnetic fields. One field is located on the rotor, which is the moving part of the motor. The second magnetic field is located on the stator, the body of the motor. Usually one of the two is generated by a permanent magnet, while the other is generated through an electromagnetic solenoid. The magnetic field generation, the relation between electrical energy, which is current, and magnetic field generated by the solenoid coil, is obtained through the formula B equals Ki of pH. The torque, which is the output torque of the electrical motor, depends on the intensity of the rotor and stator magnetic field and on their phase relationship. So the angle theta between the two magnetic fields is named load angle, and the maximum output torque and the maximum efficiency is obtained when the load angle is 90 degrees. So the basic principles of motor design methodology for the unmanned autonomous system is based on the electric motor operation with the following points of interest. At least one of the two magnetic fields is generated by a solenoid carrying a current, and the phase relationship, that is the rotor and stator magnetic field, such as the load angle, must always be greater than 0 degrees in order to keep the motor in motion. That is, negative angles reverse the rotation. The output torque depends on both solenoid currents and the angle and the load angle, and the motor rotation causes a back electromotive force opposing the motion itself. A pulse width modulation (PWM) signal is a method for generating an analog signal using a digital source. A pulse width modulation signal consists of two main components. They define its behavior, which is a duty cycle, and frequency. The duty cycle describes the amount of time the signal is in a high on state as a percentage of the total time of it takes to complete one cycle. The frequency determines how fast the pulse width modulation completes a cycle. So therefore, how fast it switches between how high and low states. It is done by cycling a digital signal off and on at a fast enough rate. With a certain duty cycle, the output will appear to behave like a constant voltage analog signal when providing power to the motor. In this application, the pulse width modulation duty cycle is used to vary the speed of the motor by controlling the motor terminal voltage. The motor voltage and revolutions per minute obtained at different duty cycle rates. As the duty cycle rates increase, more voltage is applied to the motor. This contributes to the stronger magnetic flux inside the armature windings and the increase of RPM. The rotor is composed of a group of coils. The rotor coils are sequentially connected to the motor leads through mechanical switches, brushes. The stator magnetic field is generated by a permanent magnet. The torque applied to the rotor is the highest possible because the load angle theta is about 90 degrees. Forcing a current in the motor causes the rotor to generate a magnetic field. Flight control dynamics. Each motor spins in the same direction as its diagonal counterpart and in the opposite direction of its horizontal and vertical counterparts. The rotors on each motor produce a thrust and a torque around their center of rotation. That is the direction, yaw, vertical inclination, pitch, and horizontal inclination, roll, and altitude of the drone are all controlled by manipulating the velocity of the motors with respect to each other and to the force of gravity. When all four motors rotate at the same speed, the drone autonomous system can move up or down or hover. Global positioning satellite is based on time and known positions of GPS satellites. These satellites, deployed in orbital space, carry stable atomic clocks which are synchronized with each other and with ground clocks. The satellite locations in orbital space are known with great precision. Each GPS satellite continuously transmits radio signals containing current time and data about its position. The artificial intelligent drone triangulates four of these satellites. The GPS receiver on the Smart Intelligent drone monitors multiple satellites and solves equations to determine the precise position of the drone GPS receiver. Therefore, four satellites are in view for triangulation of the receiver for the drone to compute four unknown quantities, that is, 3 position coordinates and clock deviation from satellite time. The intelligent drone GPS receiver measures the time of transmission of 4 satellite signals from the time of arrival and time of transmission. The receiver forms 4 time of flight values which are equivalent to receiver satellite ranges. The drone receiver computes its 3-dimensional Cartesian coordinates and clock deviation from the 4 TOFs.
Radio controlled transmitters and telemetry used in Corp-Inteltech smart drones. They include 3X accelerometers, 3X gyroscopes, a compass, and a barometer. These are the sensors used supporting the telemetry system. There is also an RF24 module
and the control servos. set of differential equations in order to provide stability to the drone flight. It creates complex mathematical algorithms of how machines behave.
Radio-controlled transmitters and telemetry used in Corp Inteltech smart drones. They include 3X accelerometers, 3X gyroscopes, a compass, and a barometer. These are the sensors used supporting the telemetry system. There is also an RF24 module. GPS is also supported. With our software environment, our global positioning system is programmed to display flight in progress, including displaying flight path, the technologies for pitch, elevation, yaw, which is rotating clockwise or counterclockwise, roll for left or right, and transmission of sensors. Air flight and control coordinates. Activate gyroscope and telemetry system. Ready for demo flight. Drone is ready for takeoff. Flight is on time.
Software platform for the smart drone consists of complex mathematical algorithms, sophisticated software models, and modules. Many of these modules are developed with Python and C++. The main objective is to provide the control environment for all quad motors, for all 4 motors and sensors, including as well the gyros, the radar, and the telemetry system. Here is an illustration of the software models which activate the motor movement for the intelligent drone system. The software integrates solutions for pulse width modulation by controlling several analog ports located on the main computer digital intelligent platform. The neuromorphic smart drone platform and pipeline includes GNSS, the gyros and inertial measurement, by navigation, direction, and vehicle inertial guidance with precise accuracy. The hardware subsystems are used to include radar systems. Using this data, the processor provides 3D information implementing object identification, motion vector determination, and collision prediction. Deep learning implies to the number of layers through which the data is transformed. The CAP is the chain of transformations. Deep learning algorithms are applied to unsupervised learning tasks. Cognitive neuromorphic artificial intelligence algorithms are used in order to provide control techniques for the servo motors, stimuli. The Quaternion Kalman mathematical models are used in the engineering prototype, as I have shown in this video, in order to filter out different types of environmental noise conditions introduced by the magnetometers, the gyroscopes, and the accelerometers. Error correction and error detection. Mathematical models. Data fusion based on Kalman filter. A data fusion method based on the Kalman filter is described in this application. So you could see that the measurements of the accelerometer and magnetometer are used as the input of the two-step geometrically intuitive correction. To produce the computed Quaternion. And the computed Quaternion is used as the measurement of the line Kalman filter in order to correct the predicted state obtained by using the output of the gyroscope. Quaternion Kalman filter for real-time estimation using geometrically intuitive correction algorithm. In this algorithm, the sequential geometrically intuitive correction is used to make the estimation of pitch, roll, immune to magnetic distortion. Meanwhile, the software algorithm produces a Quaternion input for the Kalman filter to reduce linearization, error of measurement equations. The artificial intelligence algorithms used in these smart drone application include object classification, obstruction identification, mapping localization, dynamic modeling, signal detection, path planning, and decision making. The inertial sensory systems contain the firmware and the software algorithms to enable the gyroscope, the accelerometer, digital compass, and the digital motion sensors. The artificial intelligent autonomous drone prototype demonstrates how it navigates by using the onboard global positioning satellite system, the gyroscopes, the accelerometer, and the inertial measurement system in order to provide navigation, direction, and vehicle inertial guidance with excellent accuracy, including object identification, motion vector determination, and collision prediction, as noted in this demo prototype and as you are currently viewing in this video.
Smart drones, robotics, and satellites.